Hello everyone, this is chapter 10.5 and here we'll be discussing conic sections. Now, a conic section is just a cross section between a plane and what is known as the double cone. So a double cone is this three-dimensional object here that I've copied 3 times, and we're going to pass a plane through it in a very particular way and we'll get an image. So I'm going to do that 3 times because there's 3 different conic sections. Well, there's kind of 4, but one is a special case of one of them. So we'll see that. So first off, if I pass the plane through one of the cones like this, the cross-sectional image you get is this kind of oval shape, which is known as an ellipse, of course. Now, if I didn't do it diagonally, but I just did it like straight parallel to the base of the cone, well, what you end up getting actually is a circle, and a circle is just a special case of an ellipse. So that's what I meant by the 4th one. What else? Okay, let's say we pass a plane through this top cone only, but parallel to the angle of the cone itself. So in doing that, you actually won't pass through the other cone, you'll only pass through the top one. And the image you get here is this shape. By the way, these images are all indefinite in each direction. Meaning that the cone extends indefinitely in each direction, the planes also extend indefinitely in each direction. The only thing that doesn't here, I guess, is the ellipse, but here what we end up getting is this U shape, and this is actually, it's a parabola. And the parabola, notice it goes off indefinitely. All right, now the last one is, what if we cut a plane that passes through both cones? Well, we end up getting our opposite facing parabolas, so I guess I should have listed the previous one as parabola. And these opposite facing parabolas are known as one unit as a hyperbola. Okay, now with each of these sections, each of these conic sections, we'll be discussing their equations as well as particular objects of their graphs of the equations. Like for example, the vertex of a parabola is an object of the graph of, well, the parabola. Anyways, we'll take a look at each one. So first we're just gonna go in order here. So I'm gonna start with ellipse, then we'll discuss parabola, and then we'll do hyperbola. Actually I'm gonna discuss parabola first because, well, we'll kind of see why. Basically, for parabolas, the equation's a little less intense and actually builds up more if we discuss it in this order. So just to clarify, we're gonna discuss this one first, then ellipse, then hyperbola. I like that order better. So let's talk about parabolas right now. All right, so for parabolas, we'll be discussing these 4 different cases. There's 2 for vertical, 2 for horizontal, of course. And by the way, for every conic section we'll be seeing in this section 10.5, will only be purely vertical or purely horizontal. That's not to say that there don't exist others, like you can take a look at a parabola that's tilted a little bit, but its equation is too non-standard and it deviates too far from what we want to see in this section. So anyways, with that out of the way, let me try to classify a few things here. So first off, there's kind of a divide. So vertical parabolas have this equation, horizontal parabolas have this equation, but there's 2 different scenarios for each one, and that's the following. It's all based on P. So if P is positive, the parabola opens in the positive direction. So either positive y direction or positive x direction. Okay. If P is negative, similarly, it will face in the negative direction. All right. And what you'll notice when you kind of compare these is that the, x and h always go together, so you'll always have x minus h, and y minus k always go together, so you'll always have y minus k. So you'll never have like y minus h or x minus k or something like that. Also, the one that is not squared, y in this case, is reminding us of the direction that we're opening towards. So in the y direction, basically. All right. Similarly here, the one that's not squared is x, so this x reminds us of horizontal, so this would represent a horizontal parabola. So that's something to keep in mind. Now what I have listed here below actually is true of any of these parabolas. So the vertex is labeled h, k, so no wonder why h goes with x and k goes with y, because h is the x value of the vertex v, and k is the y value of the vertex v. Also, the absolute value of p is the distance from the vertex V to what is called the focus, F, and the directrix, D, but in the opposite direction. So to understand what these things are, I'll have to use one of these. I'll use this horizontal one. So we can try to imagine what it will be like for the other ones, but if I draw it for each of them, it'll be a little too cluttered of an image. But let me just say this. First off, this is the vertex that will label the point V, and a distance P away from the vertex in the direction of the opening, so absolute value of P, in the direction of the opening of the parabola is the focus F. If you travel in the opposite direction, the same distance, absolute value of P, you arrive at the directrix, which is not a point actually. The directrix is a line. And in this case, the line is vertical. In the case for vertical, the lines will be horizontal. Basically, you want to draw either a horizontal or vertical line, but you don't want to intersect the parabola. Now, the big deal with, let me try to see if I can use a different color here. The big deal with the behavior between the directrix focus and, well, I guess the parabola are the following. And this, to be honest, we won't really use at all, but it's a nice feature which allows us to understand why we care so much about these objects. And this is not going to be to scale, so what I'm about to say won't really work. I'll try to maybe adjust it, but let's see. So if you pick any point on the parabola, yeah, this will have to be like way wider for us to actually see it. So I'm going to try my best to make it as accurate as possible so you can understand what I'm talking about. So let's imagine that's the parabola. And if you pick any point on the parabola and connect it to D to form a perpendicular angle, so the shortest distance to D from that point, and connect that point to the focus, doesn't quite look like it here because my scaling's a little off, but they should have the same distance. And that's for any point on the parabola. So with that in mind, these equations actually fall out. So this is like the main geometrical feature of parabolas, which I guess brings up the importance of focus and directrix. But for our purposes, all we really need to know is focus is a point that's in the direction of the opening, D is a line. It's the opposite of the orientation of the parabola. So in this case, we have horizontal, but the directrix is vertical. Here we have vertical parabolas, but the directrix will be horizontal actually. And it'll be the same distance from the vertex to the focus, but in the opposite direction. That's really all I want to say about this. Now let's move on and actually see an example. We're going to see two types of examples. One will be given an equation and we'll ask to find objects. Another one where we'll be given a description of the graph, probably the objects, and asked to find the equation. So let's take a look at that. All right, before moving on to these next examples, I want to say that something I didn't mention previously, and we'll kind of see that a little bit with ellipses and for hyperbolas as well, even though I may not actually write those specific forms. When h and k are each 0, then the vertex would be 0, 0, and the formula will simplify, or the equations will simplify, that is, a lot more simply. And you'll see some examples of this in the book when doing homework problems, but just imagine that if you don't have h and k where you expect them to be, then they're each 0. And again, that goes for ellipses and hyperbolas as well. But anyways, let's move on with these problems here. So we're asked to find the vertex, focus, and directrix for each of these equations. For this one, it becomes a little obvious because it's in the form we want it to be. So if you kind of just recall the equation that it best fits, it's of the form x minus h squared equals 4p times y minus k. So we can actually find p right away because we get 4p is equal to 8. That means p is equal to 2. Good. Also, it's positive, so that means the parabola faces either up or to the right. Since x is squared and y isn't, it's vertical. So this tells me that the focus is going to be actually 2 above the vertex. So f is 2, let me write arrow up above the vertex. Maybe that helps. What else? Well, okay, the vertex we can actually find pretty easily because if you just look at this, x minus negative 2 is the same as x plus 2, so h right away is negative 2. And similarly, k, Well, k is just 3 because y minus 3 is the same as y minus k, so k is equal to 3. So we actually have a vertex is negative 2 comma 3. That's one of the things we wanted. And if you actually graph this, and again, we know it's a facing up parabola because the number in front is positive. P is positive in this case. Also, y is not squared, so it's vertical. So we know it's vertical. We know it opens up because P is positive. Opens up. So if you go to the vertex, negative 2 comma 3, which is over here, let's say, that's the vertex, the parabola opens up, something like this, and we know the focus is 2 units away from the vertex in the direction of the opening. So if we travel 2 more units above this vertex, we arrive at this point here, which is negative 2 comma 5. So now we know the focus is negative 2 comma 5. Probably should have made more space for these problems, but that's fine. And similarly, the directrix is just the horizontal line. Remember, horizontal lines have the form of y equals a number. And it's going to be 2 units below the vertex, which will pass through y equals 1. So it'll have the equation y equals 1. So the directrix is the line y equals 1. Perfect. Now notice we kind of had to graph to see that. There are non-graphical ways of doing it, but to be quite honest, the best is to graph, and that'll help the visualization. I don't know if I have space for 2. I may need to erase some things. You know what, let me do this. I'm going to erase 1, shift 2 over here so we can use more space above. I don't want to erase this example yet because we haven't even started it, of course. So let me erase part 1 of the first example and move 2 over, and then we'll start this next example after completing part 2 of this one. So let's do that right now. All right, so here's number 2 now shifted over, and the first thing you'll realize is that it's not in the form we like part 1 was. So, unfortunately, we have to complete the square. There's no other way. Well, there may be other ways by kind of comparing to the form, but really we're just completing the square. So I'm going to move both of these to the other side by subtraction, negative 2x minus 1. And this is going to be y squared plus y squared plus 6y, I should say, plus something. So I'm going to add some number to both sides to make this whole left side a square. Let's see. So first off, if you remember completing the square methods, we know it's going to be y plus 3 all squared because it's half of the middle one. And if you FOIL this out, you'll get y squared plus 2 times 3y, which is 6y, good. And then plus the last one squared is 3 squared, which is 9. So we want this to be a 9. Okay? It does a few things for us. First off, it does this. Secondly, if you combine these two, these combine to just 8. And we don't want a number in front of x, so we want to pull that out. If you pull actually, it says positive 8 by the way. If you pull negative 2 out, you'll have x minus 4. And I hope that makes sense because when you distribute negative 2 back in, you get negative 2x and positive 8. So there you go. So now this is in the form we like. So now we can do the same thing we did with part 1 and try to go from here. The only thing is that y is squared, not x. So this is actually a horizontal, just by inspection, parabola. And this right here is negative, so p is negative. So the number in front of the non-squared term is negative. So that means p will be negative, which implies that it faces in the negative direction. So it actually faces left. Right? Left is in the negative direction for horizontal. So these are 2 big key themes we know, so we can help the rest out with the visualization. Also, we want to get y minus something and x minus something. This one's very straightforward. It's x minus 4. So that means h is equal to 4. Because remember, it's always x minus h, always y minus k. So now notice, y plus 3 is the same as y minus negative 3. So that means k is negative 3. Perfect. So now from both of these, we have the vertex is the point 4 comma negative 3. Awesome. So now with that being said, I guess we need to find p, don't we? I guess I have some space here. So the number in front is 4p. So we're going to write negative 2 is equal to 4p. Divide by 4 to get p. We get p is equal to negative 1/2. Which isn't the best thing because you have to travel a distance of a fraction, but it's not too bad. It's a kind of nice fraction, I guess you can say. So let me try to draw this appropriately. So we're going to go to 4 comma negative 3. So let's say this is 1, 2, 3, and let's say that's 4, and then down 3, 1, 2, 3. That sounds okay. So this is the vertex, and it's going to open to the left. Horizontal opens to the left. So it'll look something like this. Okay. So now what? Well, now we're going to travel in the direction of the opening of the parabola, a distance of 1/2. So, because that's the absolute value of negative 1/2 is 1/2. So if you travel 1/2 in this direction, you actually land at, well, 3.5. So this point right here, very, very, very close to V, is the focus. So the x value is 3.5, but notice the y value is still a negative 3. So from this, we get that the focus is the point 3.5 comma negative 3. Or if you like, 3.5 is 7 over 2. So I prefer that actually. I'm going to write 7 over 2 because I like fractions. But that's just me. If you want to write 3.5, go ahead, it's fine. That's the focus. The directrix is also not too bad to find because we travel in the same distance we traveled for the focus, but in the opposite direction, away from the focus from the vertex. So this is going to be 4.5. And it's a vertical line. So let me move V. So this is the directrix D. And a vertical line will always have the form x equals for its equation. So this is going to be x equals, so for the directrix, it's going to be x equals 4 plus 1/2, which is 4.5. But I'll write it as a fraction 9 over 2. Perfect. So there we go. We found the focus, directrix, and vertex for each of these parts for this example. So now moving on to this one, it's a little different. In fact, I think it's a little easier in my opinion, but we'll still have to use some graphing to figure out what's going on. So first off, h and k are given right away because we have the vertex. That's a lot of power right there. The other thing is we don't know if it's vertical, we don't know if it's horizontal, we don't even know what direction it opens. But once you start to plot these, it'll become a lot more obvious which of the 4 it is. So let's plot these. Negative 3 comma 0 is over here. So that, let me label that as V. Negative 3 comma 2 is 2 above that. And that's F for focus. Now just looking at this, what do we know? We know that this has to be vertical and it has to open up. The parabola has to look like this in order for the focus to be directly above the vertex. So the, I guess, orientation of focus and vertex will tell you exactly the orientation of the parabola. So that's pretty neat, actually. So from this, we know that, well, it's a vertical parabola, and we also know that P is positive. And furthermore, we actually know the distance. We know the absolute value of P is 2. Because remember, the distance is the absolute value of P. Since P is positive and the absolute value of P is 2, these just mean that P is positive 2. If it was negative and the absolute value of P was 2, then it'd be negative 2. But in any event, we're there. Vertical, what does vertical say to use? Vertical says to use the equation x minus a number squared equals 4p times y minus a number. So that's the equation we'll be using for vertical. The opposite letter x would be squared. Vertical, we think of y. So the non-square is y, basically. All right, so now we know h and k. So this is x minus h squared. So that's x minus negative 3. 4p, that's 2. And y minus k, that's 0. So this is going to be x plus 3 all squared equals 8 times y. Awesome. So there we go. That's the equation of the parabola. That was pretty simple, actually. And it's kind of neat because we see a lot of the graphing helping us out there. So graphing these things will definitely help find one or the other. So find the objects or versus this, finding the equation. So now let's take a look at ellipses, and then finally we'll look at hyperbolas. All right, so now for ellipses, there's a lot to say here. First off, you'll notice that there's actually only two cases, and there's not two cases for each of them like there were for parabolas. Parabolas actually only had either a vertical axis of symmetry or a horizontal axis of symmetry, if it was vertical or horizontal respectively. But actually for ellipses, well, there's both for either case, meaning there is a vertical axis of symmetry and a horizontal axis of symmetry. So if you flip this vertically or horizontally, across these axes of symmetries, then you'll get the same image. And that's true of this one as well. By the way, notice that there is a longer axis and a smaller axis. So the larger one is known as the major axis, where the smaller one is known as the minor axis. So notice capital M for major and lowercase m for minor. Now, where the ellipse intersects the major axis, these are called the vertices, and vertice is just plural for vertex. So I'll label these points in blue as V1 and V2. Okay. Now, where the axes of symmetry, where they intersect, this is known as the center of the ellipse. And I want to use capital C, but as it turns out, we'll be using lowercase c sooner or later. So we'll be using lowercase c as well. So for that reason, I'm going to try my best to distinguish between the two by putting like a little curl on that capital C. So I advise you to do the same. Right. And the points that intersect the ellipse and the minor axis are known as minor axis endpoints. That if you want, you can label as M1 and M2. But to be quite honest, we won't really be using these at all. But it's helpful sometimes to have labeling anyways. But it's up to you, really. Now, the distance from the center to a minor axis endpoint will be B. And the distance from the center to a vertex is going to be A. So this is A. This is also A, but I'll label one of each. And this is B. Now, I said we'll be using lowercase c. So to use lowercase c, we need to introduce one more thing, and that is focus. But there's two. There's kind of a pair. Just like vertices, there's a pair. So the top focus, so plural for focus, by the way, is foci, spelled F-O-C-I. Some people pronounce it foci. As it turns out, both pronunciations are acceptable. It's kind of like tomato, tomato. But I say foci. I'm just used to that. Anyways, so there's two foci. There's two of there's a pair of focus. Parafoci. There's two foci, of course. So the distance from the center to a focus is labeled as C. And it's the same distance for each. That's why I'm only labeling one of these when in fact the distances are the same throughout, because it's symmetric. It's a very symmetric image. Okay, good. So the distance from here to here, let's say, is lowercase c. Now, yes, there are only two equations, one for vertical and one for horizontal. You notice here that the distance A is always going to be larger than B. If B was bigger than A, in this case, it would actually be horizontal and not vertical. So keep that in mind. So A has to be larger than B. And we'll actually see that coming out shortly, but let me just write here. A is always larger than B. Now, with that being said, if you kind of compare the equations, you'll notice here that the larger number a squared, is always going to be under y for the vertical equation and under x for the horizontal equation. So it'll be really easy for us to distinguish between which equation represents either a horizontal or vertical ellipse. Just look at the larger denominator. If there's an x on top, it's horizontal. If there's a y on top, then it's vertical. Okay? And then there's a few things here that are in common with each of them. So let's see. So it says the center is h comma k. So notice x minus h, y minus k. Kind of like we had for parabolas with the vertex. So that's okay. And vertices are a distance a away from c. We know that. Foci are a distance c away from c, so the center. So we know that. And here c squared is equal to a squared minus b squared. This is important, super important. This will allow us to find c. Also, notice, since a is bigger than b, this makes sense. Because c squared, of course, is a real number. C is a real number. When you square a real number, it's a positive value. So a squared better be bigger than b squared, or else you'll have a negative and it won't be real. So for that reason, we need a to be bigger than b. So that's another thing to realize. And there is one more thing I kind of want to say here, but it's kind of hard for me to describe. But notice when I described parabolas earlier, I mentioned there was some key feature that makes these objects, in this case, well, in the case for parabolas, it was directrix, vertex, and focus, why they're so interesting to us. Now, for ellipses, all I want to say is this. If you pick any point on an ellipse, and you look at the distance, or I guess the perimeter, I should say, of this triangle, it will always be the same. And that connects the foci to any point. So that's why the foci are of particular interest. The center is just the midpoint between those two, and the vertices are just, well, the outermost points. So yeah, you can kind of convince yourself of this. In fact, a lot of people use this to create an ellipse. So if you think of creating a circle, you would, let's say I did it on the board here. I don't have the tools to do it, but imagine I had a nail on the board and a string of a certain length, and I connected my pen to it, and went around, I would have a perfect circle if that string remained the same length around, right? Because it's just the radius swinging around the center. But if we had two nails instead, and instead of a string, like one string piece, we had like a string loop, and I connected that to my pen to the nails, you would have this kind of triangular shape if I put it out like this, and then going around, the distance around the loop, the perimeter of the triangle, in other words, would remain the same no matter where I would have my pen. So that will actually create an ellipse. If you wanted to create a vertical ellipse, then you put the nails vertically like this. And notice the distance they are away will have a different shape of ellipse. So it's pretty interesting to see that. And you can kind of see why it's more generalization of a circle, because when the two nails would be one, then you have a circle. So it's kind of like squishing a vertical ellipse right before it becomes horizontal. There's a sweet spot, and that's a special case of the circle. And this is actually when A and B are equal, which is really, really cool when you look at it, because when A and B are equal, they are the radius of the circle. So if b squared is equal to a squared is equal to, let's say, r squared, multiplying through by r squared will give you the equation of a circle that we know and love, x minus h squared plus y minus k squared equals r squared. So that's nice to look at. Otherwise, when one's bigger than the other, you have these two cases. So I've spoken of this enough. Let's look at some examples now. All right, so for this example, we want to find the vertices and the foci for each of these equations. Now, these do not look like the form we had for the ellipse equations that we saw before. Remember that it was always 1 on one side, and then we had fractions. So how can we make this 1 for this first example? Well, if you divide everything by 9, then you'll actually get cancellation here, so you'll have 1. Here we'll have x squared over 9. These actually cancel too, so we just get y squared. Okay. Now, remember that the form we want specifically was x minus h squared over something squared plus y minus k squared over something squared equals 1. So let's fill in the blanks here. Notice x minus 0 and y minus 0 is just x squared and y squared. This is the special case that I spoke of with parabolas. I kind of mentioned it briefly, that when h and k are 0, you get a much more simplified version of the equations. And this is kind of what it would look like, kind of. So in this case, they're technically 0. The denominator of the first one is 9, which is 3 squared. Good. It's all coming together. And the denominator here is 1, which is 1 squared, technically. So we know a few things. Now remember, a is the larger one. So the larger one is 3. Now remember, it's a squared and b squared. So a is 3. Perfect. B is 1. Fantastic. Can we find c? Yes, we can, because we know c squared is equal to a squared minus b squared. We know a squared is just 9, b squared is 1, so c squared is 8. That means c is the square root of 8, which actually simplifies to 2 radical 2, of course, because 8 is 4 times 2, and the square root of 4 is 2, so 2 comes out. So let me write that all together. C is 2 radical 2. All right. What else do we know? Oh, we know the vertex, not vertex, we know the center. The center is what point? Well, it's h comma k. Remember, this is h, this is k, so our center is the point 0, 0. So that's important too. So we can actually begin to try to graph this to see if we can kind of count to see where our vertices and foci will be. So let's see if we can do that off to the side here. I'll try to make some space and make it a little more straight. I think that looks a little better. Okay. So first off, the center is 0, 0. Is it a horizontal or vertical ellipse? Well, the larger number is under x, so this is for sure horizontal. So we're going to go to the distance 3. Another way to think of it is that 3 squared is under x, so you go left and right 3. 1 squared is under y, so you go up and down 1. That's another way to think of that. So you go left and right by 3. There we go. And then you go up and down by 1. Let's say this is 1. It's not quite to scale, but it's close. So we get this nice elliptical shape. Looking pretty good. Now, with that being said, we actually know what the vertices are. These are the vertices. So let me do this. Let me write over here. Our vertices are going to be, let's say V1 is the first one, and V2 is the second one in that order. So V1 is negative 3, 0, where V2 is 3, 0. Boom, there we go. Those are the vertices. But now we also want the foci. We know the distance from the center to the focus, to any focus, is 2 radical 2. All right, so, well, where 2 radical 2 exactly is, you can use your calculator. It's about 2.8. I just know that because radical 2 is about 1.4, and double that's 2.8. So it's going to be really close to 3 here and here. So in any event, you can label these. So this is F2 and F1, let's say. And by the way, the labeling doesn't really matter as far as which one you label as which. But let me just write it over here wherever I have space. F1 is the point 2 radical 2, 0, where F2 is the point negative 2 radical 2, 0. If that looks okay? Awesome. I'm just boxing each of them. And there we go. So those are the vertices and the foci for problem 1. Problem 2, we're going to go through the same motions, but this should remind you of something we saw with the parabola examples we looked at earlier. We have to complete the square here because there's x squared, y squared, much like there were here, but there's also this x we need to get rid of, and we can only do that by completing the square. The other thing is that we have these pesky coefficients of the square terms. So here's what I'm going to do. For the x's, I'm going to factor out 9. When you factor out 9, you get this. Yeah, it's an x. All right. So the other thing to remember is that we want to add and subtract some number to make this a square. And it's half of the middle one squared. Half of the middle number is negative 2. Squared is positive 1. So if you add and subtract 1, this becomes, well, x minus 1 all squared, then minus 1 all times 9. And then the rest is the same. So plus 4y squared equals 27. Plus 4y squared is equal to 27. If you distribute the 9 like this, you get 9 times the quantity x minus 1 squared minus 9 plus 4y squared equals 27. If you add this 9 to the other side, you get 36, which just so happens to coincidentally be 9 times 4. That's good. So we divide everything by 36 to make this a 1, kind of like we saw over here. Then we'll get our standard form that we were looking for. So notice 4 goes into 36 9 times, 9 goes into 36 4 times. So we get x minus 1 all squared over 4, which is 2 squared, plus y technically minus 0 squared over 9, which is 3 squared, is equal to 1. So now we're going to use this to find the vertices and the foci like we did over here. It's going to be a little more involved because the center isn't just the origin. Yeah, it's not too bad as it turns out, but I definitely need more space. So here's what I'm going to do. I'm going to erase everything. I'm going to grab this result here, shift it over here somewhere, and then we'll move on. Right, so this is the result we just ended with just now. And we want to find these objects, the vertices and foci. So first what I'm going to do is find the center. So notice the center is just h comma k. So in this case it's 1 comma 0. Notice it's positive 1 or negative 1 because it's always x minus h, right? Just keep that in mind. A, which one's A? A is the larger one squared, so that's going to be 3 squared, so A is 3. A squared is the larger one. B is going to then be 2, perfect. And then we can find C, because we know C squared is A squared minus B squared, which is of course 9 minus 4, which is 5. So that means C is just the square root of 5. So we have all of these lovely facts here, but we're going to use these to somehow find the vertices and foci, but we have to sketch the graph to really figure out what's going on. So let's do that here. So first off, I want to get to the center. The center is 1 comma 0, which is over here, let's say. And we're going to go, let's see, under x is 2 squared, so we're going to go left and right by a distance of 2. So that's going to leave us with, at this point, and if we go 2 in this direction, we'll have negative 1, which is that point. Okay, so far so good. Then we're going to go up and down a distance of, so this was the center, by the way. And we're going to go up and down a distance of 3, which is the number squared under y. So if we go up 1, 2, 3, we land at this point. If we go down 1, 2, 3, we land at this point. So it may be hard to tell with my scaling, but the longer ones, the longer of the two, the further ones further away from the center that is, are these two vertically. So these will be the vertices. And that'll be our image like that. Let me try to do that a little more justice. It looks a little better. It still looks kind of circle shaped. It should look more vertically oblonged. But that's fine. I'll just leave it like that. Now what? Oh, now the foci lie on this major axis where the vertices are located, by a distance of radical 5 away from the center. So we go up by a distance of the square root of 5. We'll get the first focus. If we go down by a distance of radical 5 also, we get the second focus. So this is just to illustrate how it looks. I'm not being accurate with the with where the value is like it was with the previous part 1. But anyways, this actually tells us right away what the vertices are. So the first one is 1 comma 3. The second one here is 1 comma negative 3. So 1 comma 3 and V2 is 1 comma negative 3. What we called F1, the first focus, was x equals 1 comma, going up a distance of radical 5 from the x-axis, just gives us radical 5 for the y value, the x value is to 1. So this is 1 comma radical 5. Similarly, for the second focus, we go down from the x-axis. So that is 1 comma negative radical 5. And we are done. These are the 4 things we wanted to find. And I guess I'll box them separately like I did the previous one. And that's the only example I want to do for ellipses. And now let's move on to hyperbolas. There's a distinct difference in the equations, and the graphs look dramatically different. So let's take a look at that. All right, so now finally for hyperbolas, you have opposite facing parabolas. So much like with ellipses, actually, there's 2 axes of symmetry. There's the vertical and the horizontal for each. So if you flip this image vertically or horizontally, it'll have the same image. Similarly for horizontal. Now I kind of just want to cut to the chase, to be quite honest, because as it turns out, the objects here are the exact same for that of an ellipse. There is something else that are known as the slant asymptotes, which will just help you draw a better image or a better graph, that is. And then there's something that's known as the inner box, which really just tries to mimic, the ellipse, because the horizontal points, well, not horizontal, but the non-vertice points of the parabolas, which would be these guys here, basically act as minor axis endpoints, in the sense that the distance from the center to one of these points is b. So that's something you can kind of use to help draw a better graph, but I'm not going to really talk about that too much. What I want to talk about is basically how this relates to what we saw in ellipses, because how it behaves as far as finding the objects go is exactly the same. The only real difference is that the equations are tweaked a little bit, and so is this formula here, so we'll talk about that. So as far as the objects go, let me just label them in red, for this one anyways. So we have the center, which is capital C. We have the vertices, just think of like vertex of a parabola, but there's two of them. So let's call them V1 and V2. And again, which one you call V1, which one you call V2, doesn't really matter, but I'll just go from left to right. And then again, much like with parabolas, each parabola has its own focus, which together, plural, is just foci. And yes, the distance from the center to a vertex is A, and the distance from the center to a focus is C. Now you can kind of see here, this is kind of the reason why B is not really too important, because as it turns out, the wider the parabolas are, B could actually be larger than A in this case, but C is always going to be larger than A. So with ellipses, A was always bigger than B. That's not the case here. So keep that in mind. Let me just write, A is not necessarily greater than B. It can be, but not necessarily bigger than B, contrary to ellipses. Now let's talk about the equations. So the equations for vertical, well, it looks just like, in fact, both of them look just like the ellipse equations, only you'll notice right away there's a minus instead of plus, and that's what most people think of right away. But there's a little more to it. So notice that the one under y squared is a squared, the one under x squared is also a squared. So it kind of seems like it's trying to do what the ellipse was, but it's a little different because remember, A isn't always the larger one. B could possibly be bigger than A actually. So in fact, what we'll be doing here is just looking at subtraction. If x comes first in subtraction, it's horizontal. If y comes first in subtraction, then it's vertical. So that's what we're looking for. Which one comes first? Not the larger denominator. So that's one of the key differences between ellipse and hyperbola equations anyways. Now everything else is basically the same. H comma k is the center. The vertices are a distance A from the center. The foci are a distance C from the center. We already said that. Now this equation, unlike the ellipse equation we had was c squared equals a squared minus b squared, here this is c squared equals a squared plus b squared. Very fitting because it's opposite of the sign we had here for the equations, much like with ellipses actually, if you take a look back at that. Alright, so I've spoken enough about this. We're actually going to do some examples involving these hyperbolas, and that'll be it for this video. So let's take a look at those examples right now. Alright, so for these examples now we're going to do exactly what we did with ellipses. We're going to find the vertices, foci, and yikes, we're actually going to find the asymptotes. I briefly spoke about the asymptotes. I didn't tell you how to find them, but now that we have an idea of what they are, kind of, they're the intersection of that box, the corners of that box I was talking about. I'll dive deep into that for each of these examples, and we'll see it's not really too bad actually. But anyways, let's dive into this. So first off, much like what we saw with the ellipse examples, we need to write them in the form that we saw for the equations. So we need these numbers to be ones on the other side. So let's start with this one, of course. So divide everything by 100. We'll get x over 100. By the way, x is the same as x minus 0 squared technically. Over 100 is 10 squared minus y minus 0 squared over 10 squared as well equals 1. So that's kind of the main goal here, to get it in this form. So notice I add the minus zeros just to understand what the center is. So remember the center is h comma k. So the center right away is going to be 0, 0. Also, the one under the first term in subtraction is a. That's how you know which one's which. It's not the larger one. It's the one that's under the first term in subtraction. It's always a then b. So a squared is 10, so that means a is 10. B is also coincidentally 10 in this case. So we have these three. A and B will help us find C. Remember, c squared is equal to a squared plus b squared. So that's going to be fun. That's 100 plus 100, which is 200. And the square root of that is the square root of 200. Since 200 is 100 times 2, you can square root 100 and get 10. So this is really just 10 radical 2. Awesome. Now we'll have to graph to figure out exactly what's going on. Notice x comes first, so this is indeed going to be a horizontal hyperbola. So let's see if we can actually graph here. Maybe I'll graph here just so I have space to talk about the asymptotes. I think we'll have enough space here. So the origin, let's say, is there, and we're going to go up and down by a distance of 10. Now, like I said, I briefly mentioned the box, but here with this example, I'm going to show you exactly how to specifically and accurately graph the hyperbolas. So instead of creating an ellipse like we saw from ellipses, we're going to create this dotted box here, just like that. Imagine that's a better box. There we go. In this case, it's a square because all of the side distances are the same. And since this is a horizontal hyperbola, well, the horizontal points here will actually be the vertices of the hyperbola. So the hyperbola will look something like this. Right? And the vertices we can clearly tell are 10, 0 and negative 10, 0. So v1 and v2 is just, let's do a negative 10, 0 and 10, 0. By the way, some people write this all together as plus or minus 10, 0, which I'm kind of tempted to do, but you can do that if you want. But I'm just going to box these for the vertices. Good. For the foci, well, the distance from the center would be c for the foci. So that's 10 radical 2, which is, of course, bigger than 10, which we expect because otherwise it's not inside of the opening of the parabola, which we want it to be. So we're going to travel the distance of 10 radical 2. So let's just say that's this point here. So this line is supposed to be an extension of the x-axis. There we go. And let's just say this is a 10 radical 2. And this is the second focus, if this is the second vertex, and so on. And so F1 would actually be the first one here, so it'd be negative 10 radical 2, 0. And then F2 would then be positive 10 radical 2, 0. And there we go, these are the foci. Now, the only thing that's still a mystery to us is, of course, the asymptotes. But here's all I'm going to tell you. The asymptotes connect the corners of this box that pass through the origin, pass through the center. So remember, here, this is the center that I'm labeling in blue. So this will be one of the asymptotes, like that, and the other one will be over here. There's actually a really quick way to find the form of the asymptotes. Notice they're actually going to be perpendicular always. And the reasoning here, well, if you just kind of take a look, the slope of this first one, I guess we can label them as asymptote 1 and asymptote 2. Let me do that. So this is A1 and this will be A2. Now the equation for A1, well, its slope is negative. And if you kind of look at this point here that it passes through, it goes down 10 over 10. Negative 10 over 10 reduces to negative 1, so the slope is negative 1. Its y-intercept is actually 0, so the equation here will just be, well, it's going to be y equals negative x plus 0. So the A1 equation is going to be y is equal to negative x. And similarly, for the A2 equation, you kind of see it already. It's y equals, again, I'm using the mx plus b here. So the slope is positive 10 over 10 up 10 over 10, that's 1. So it's 1x, plus the y-intercept is just 0. Now, the y-intercept isn't always the center. We got kind of lucky here. But in general, what you can actually use is point-slope form to find the general equation for the asymptotes. But I think doing this is okay, and it's not too much more than what we already did anyways. For 2, here's what I'm going to do. I'm going to write this in this form, kind of like we saw for ellipses. We're going to have to complete the square, of course, but you probably noticed that would be happening. Based on the previous example we saw for ellipses, I won't have space to do all this, so I'm going to erase after I do the result, find the result. So let's do that. So notice I'm going to complete the square with y's. Also, there's a negative in front of y squared. I don't like that. So I'm going to pull the negative in front of the y squared out. That'll change the sign of this -2. Well, this positive 2y to negative 2y now. And I want to add and subtract some number to make the first 3 terms a square. And this is actually the same completing the square we got from the previous example. And that's for ellipses, and that was +1 - 1. Because it's half of the middle one squared, which is -1 squared, which is +1. So you add and subtract 1. That'll make this y - 1 squared. If you distribute this negative into, again, these 3, which is just this, and this 1, that's -1, so now this is +1. X squared is here. This is 2. If we subtract 1 to the other side, we get x squared, which is x - 0 squared, technically, over 1 squared, minus y - 1 squared over 1 squared, technically, equals 2 - 1, which is already 1. Which I kind of saw ahead of time, which allowed me to jump right into the squares. Otherwise, if it wasn't 1, you'd have to divide by it, kind of like we divided by 100 here. Anyways, this is the equation we'll be using. And we can actually find a lot of things out from this, but again, I want to make more space. I'm going to erase all of this and write this over here. Alright, so here we are. Now, unfortunately, this is also horizontal, so we don't get a taste of each example, but that's okay. How we know it's horizontal, again, is because x comes first. So let me just write this is definitely horizontal. It's a key fact. The center we know, again, is h, k. The one that x is being subtracted by, and then the one that's being subtracted from y. So that's 0, 1. A is the first number squared, so that's 1 squared, so it's 1. And the second one is b. It's always in that order, a, then b. So they're both 1. That means c squared is 1 squared plus 1 squared, so it's just 1 plus 1, which is 2. So c is naturally the square root of 2. I think we're all set. I think now we can just start graphing to help us out in finding these pieces here, these objects. So let me draw an XY plane over here. My marker's already getting kind of dull, but it still comes out on the picture here, so that's okay. So first I'm going to go to my center, which is 0, 1, which is up here. And now we're going to do the same thing I did previously. We're going to find that box. Now in this case, the denominators are both 1, so it's going to be a square. And in this case, so we're going to go up 1, down 1, right 1, and left 1. Now what's funny here is, like I said this won't always happen, but I may have actually said it wouldn't happen for this example, but it actually does. The center is still on the y-axis, meaning the asymptotes will actually be pretty simple to find because we know the center is just going to be the y-intercept of the lines. So that part will be okay. Now, if you go horizontally, these will be the vertices of the hyperbolas. So they'll look something like this. So if this is V1 and this is V2, then V1 is going to be -1, 1. V2 will then be 1, 1. Now traveling from the center a distance of c, which is radical 2 in each of these directions, well, radical 2 is 1.41, so it's going to be somewhere here. So let's just say that's radical 2. And this would then be negative radical 2. It's a little closer to -1 than it is to -2, but that's okay. And then these points that they correspond to appear with the same y value because they lie on the same major axis in this case. That'll be F2 and F1, just again labeling it from left to right. And again, you don't have to do that, that's just the way I do it. So F1 will then be negative radical 2, comma 1. And f2 will be positive radical 2 for its x value, and 1 still for its y value. So something you'll notice is that the vertices and foci will all have the same y value if it's horizontal. Similarly, if the hyperbola is vertical, they'll all have the same x value because they'll all lie on the same vertical axis of symmetry, which is pretty nice to know. Gives you good insight. There we go. I was going to box this, but we need, of course, the asymptotes. Now, like I said, the asymptotes here will be pretty simple because we'll have the y-intercept. So here, these are the corners of the box. So if you connect these corners through the center, you get this asymptote and this asymptote. Now the phrase asymptote, if you don't remember from algebra, means that it approaches but doesn't touch. In fact, you see that a little bit in Calculus 1, so that's fine. But in this case, I did kind of poor job here because it looks like it intersects, but it's not supposed to. The parabola is kind of supposed to hug the asymptotes here. So if I call this first one A1 and the second one A2, A1 is going to have what equation? Well, let's see. A1 is going to have slope negative 1 over 1 because you go down 1 over 1 to get from one point to the next. So A1 is going to have equation y equals negative x plus, what is the y-intercept? The y-intercept is positive 1. And very similarly, asymptote 2 will have equation, well, the slope is positive 1 over 1 because you go up 1 and over 1 to get from one point to the next, just like this. And so that's going to be y is equal to positive 1x, which is just x, plus 1, again, because the y-intercept is positive 1. So there it is. Even though we had to discuss asymptote for these examples, it wasn't actually too bad in the end. Anyways, that concludes 10.5, and that's really it for chapter 10. Again, some courses may cover 10.6, but we're not going to cover it in this course. If you are taking a course that will cover chapter 10.6, this will only help because it introduces topics that will be further discussed, but now in polar coordinates, oh boy, in 10.6. I get chills just thinking about it. This sounds either really gross or really fun, depending on which way you look at it. Hopefully really fun. Anyways, that's it for this video. I'll see you in the next videos. See you then. Thanks for watching.